Page 1 of our notes on section 13.4 in multivariable calculus. We're going to be looking at the relationship, it's really a physics kind of a lesson, between a position vector, a velocity vector, and an acceleration vector. Let's look at this definition up here. If the position vector of a particle moving in space is a differentiable function of time, the derivative dr dt is v. That vector, it's the velocity vector. At time t, the direction of the velocity vector is the direction of the motion. And the magnitude of the velocity vector is the particle's speed. And the unit tangent vector is going to be called the direction vector. So with that in mind, we can also take one further definition. Take the derivative of your velocity vector. You actually wind up with the acceleration vector. So let's take a look at a quick example right here. Let's say we have a position vector, r of t, and we need to find the velocity, the speed, the acceleration, and direction, very particularly at t equals 2. So here's r of t right here, and of course, that's really just t to the third t squared. We can quickly find our velocity vector. Our velocity vector is going to be 3t squared, 2t. If I take another derivative, the acceleration vector then, not surprisingly, will be 6t, 2. But what we can do very, very quickly is realize that we're trying to find these vectors at a particular t value. I'm going to say over here that if I were to plug in a t value of 2, 2 squared, of course, is 4. 4 times 3 is 12. 2 times 2, of course, will get you a 4. Likewise, over here for my acceleration vector, that's going to be 6 times 2, which is also a 12, but that would be 12, 2. Now, if I'd like to know my speed is going to be the magnitude of my velocity vector here at a time of 2. And that's going to be really the square root of 12 squared plus 4 squared. Well, we know that should be 144 plus 16, which is actually 160. 160 is 16 times 10, and the square root of that will be 4 radical 10. So the speed is going to be right here. My velocity vector is the vector 12, 4. My acceleration vector is 12, 2. One more thing that we need to know is the direction vector. Well, to find our direction vector, what we are going to find is that it's the velocity vector at 2 divided by its length. We're going to have, this velocity vector at 2 was 12, 4. But of course, we're going to be dividing by 4 root 10. And you can see that's going to yield 12 divided by 4 is going to be 3, so that's 3 over radical 10. And then we'll have 4 all over this, 4 root 10. The 4's cancel out. You'll have 1 over root 10. So, both of the components, the 12 and the 4, get divided by a 4 root 10. I've divided both of those by 4. So this is your direction vector. And we're done with our first example. We've got our velocity vector. We've got our speed. We've got our acceleration vector. We've got our direction vector. Well, as we keep going here, as we look at the bottom of page 1, it says that a moving particle starts at an initial position of r of 0, and that's 1, 0, 0. I do want to point out that this is an initial condition. Our position vector is not always at 1, 0, 0. It's only when t equals 0. Likewise, we have an initial velocity. That's an initial condition. your velocity vector is not always I minus j plus k. And of course, we could look at that as 1 comma negative 1 comma 1. It's just for the briefest moment when t equals 0 that is our beginning velocity vector. But by way of comparison, the acceleration vector right here, you can look, and we need to start paying attention to this, is, that acceleration vector, it's a of t. This means that, very different from our previous vectors, this is with respect to t. So if I wanted to find my acceleration vector at t equals 0 or t equals 7 or t equals whatever value I'd like, I can plug that in and find that out. So what we're going to do nicely is we're going to say, you know what? We're going to find the velocity at time t. So if you want to find your velocity vector with respect to just time t, you might say, well, won't I just be integrating my acceleration vector with respect to t? And indeed you will. Look, your acceleration vector is 4t, comma 6t, comma 1, right? So this is going to be a vector, but it's going to be a vector of 4t dt for my x component. It's going to be the integral of 6t dt for my y component. It'll be the integral of 1 dt for my z component. So I'm integrating that acceleration vector. I have to integrate each of those components separately. And what do we get? Well, we're going to see that our velocity vector is going to be the antiderivative of 4t. Bump that up, your power to a 2, and divide. You'll get 2t squared. Take your antiderivative here, bump that up to a 2. You'll get 3t squared. Take a derivative to check that, by the way, if you're ever worried. And notice I'm going to say plus a constant vector. You could have said plus c1, c2, c3 on the interior here of this vector. It's probably just as well to just say, look, you integrate a vector, you'll get a constant. This constant would have an x, y, z component as well. But if I were to let t equal 0, then I have v of 0, right? And what do we know about v of 0? V of 0 is this vector of 1 comma negative 1 comma 1. And if I were to plug in a 0 here for what I just found, you'd say, well, my goodness, I've got the 0 vector, 0 for all the components. That's just going to wipe out. So what is your constant vector that you're going to really find that you're adding to all of your components? It's 1 comma negative 1 comma 1. Now I'm going to rewrite my velocity vector right up here. But now I'm going to say, you know what? The inside of this vector, the 2t squared, that's where I'm going to be adding a 1. That's my initial condition. Add a 3t squared here, but I'm going to subtract a 1. You can see that was my y constant component that's added in the constant vector. And then I had t. Here's a t plus 1. Guys, the cool thing is if you were to plug in a 0 right now, you would quickly see that you're getting the initial condition that they gave you. If you plugged in a 0, that's exactly what you get. If you were to take the derivative of this velocity vector, you get the acceleration vector. So things are coming together nicely. The thing is, this is part of our answer. We certainly want that. But we also want to find our position vector. And our position vector, not surprisingly, just like we learned in BC calculus, is, well, we're going to integrate our velocity vector. And of course, when you're doing that, what that really will entail, no surprise, I hope, is that I'm going to integrate each of these components, my x component, my y component, and then finally my z component. And look at this. Right now I hope it's only going to take just a slight matter of time. You bump this 2 up to a 3, you divide by it, you get 2/3 t to the third plus t. Take your antiderivative of 3t squared, you'll get t cubed, and then you'd minus a t. Take your antiderivative here, you'll get t squared all over 2 plus t. And then we'll have a constant vector. I'll call it vector d if you'd like, just to use something a little bit different. Of course, your constants would be showing up in components as well. But look, it's never a bad idea, just like we've talked last year, to keep checking that you didn't make a silly mistake. You could take your derivative right now to make sure you're back to your velocity vector. It would only take a moment to see that. But look, if we were to let t equal 0, look, you know that your initial position is 1, 0, 0. And if we were to plug in a 0 into this vector here, you'd see 0 cubed plus 0, with the 2/3 out in front. That's just a 0. My goodness, I get a 0 right here. I get a 0 for the z component. Again, that just completely wipes out. What are we getting at? Our constant vector d is very much the unit vector. It's actually just like I. It is I. It's 1, 0, 0. Well, one more thing we're going to do to get the official position vector, r of t. You pretty much had that right up here, but you know what? You're seeing that the constant that is added to your x component, you just saw that with d, is 1. You add 0 to your y component. You add 0 to your z component. Here's the cool thing. Right now, you could plug in t equals 0, and you'll see you're right back where they said you should be at 1, 0, 0. You could take a derivative real quickly and come up with your velocity vector that we just found. So really a nice lesson at this point, dealing with some problems that hopefully are going to be reminiscent to what you've done in the past.